In this video, I'll discuss related rates problems. Here are the main points to be addressed in the video. Related rates allow us to compare various changing rates in a scenario. Given a formula A equals f of b of x, the chain rule says A prime equals A prime of b of x times b prime of x. Or, alternatively, A prime equals df db times db dx. First, I'll describe how to create a formula to solve related rates problems. Here's a spherical balloon that is being filled with helium at a constant rate of 90 cubic inches per second. We would like to know how fast the radius of the balloon is changing when its volume is 246 cubic inches. If we let r represent the radius of the balloon in inches, v the volume of the balloon in cubic inches, and t is the number of seconds elapsed since the balloon started filling with air, then dr dt is the instantaneous rate of change of the radius of the balloon with respect to time. That is, how fast the radius of the balloon is changing, and dv dt is the instantaneous rate of change of the volume with respect to time. So using this notation, our goal is to compute dr dt when v, volume, equals 246 cubic inches, given that dv dt equals 90 cubic inches per second. Since the volume is a sphere, we can define a formula that relates the volume of the balloon and the length of its radius. This formula is volume equals 4 over 3 times pi r cubed. This formula alone does not tell us values of the instantaneous rate at which the radius of the balloon is changing, because the formula relates the values of the balloon's volume and its radius, not the instantaneous rates at which these quantities vary with respect to time. So, in order to answer our question, we need a formula that relates dr dt and dv dt. How can we do this? The main idea is to think of v as a function of t, because as time increases, the volume is also increasing. Similarly, we can think of r as a function of t. Then we can take the derivative of each side of the equation. On the left side of the equation, the derivative of v of t is just dv dt. On the right side of the equation, to start, we'll keep the constant 4/3 pi. Then, since we're thinking of r as a function of t, we'll need to use a chain rule. So, we'll take the derivative of outside function, so 3r squared, and then multiply by the derivative of the argument. And we can cancel these 3's, which leaves us 4 pi squared times dr dt on the right side of the equation. Then, since our goal is to compute dr dt, we can divide both sides of the equation by 4 pi r squared. Now we have a formula for dr dt that involves dv dt, which we know is equal to 90 and r. We can use this formula that relates volume and radius to find the radius when the balloon has a volume of 246 cubic inches. We can plug 246 in place of v and so for r, getting that r is approximately 3.9 inches. And now, since we know that r is equal to 3.9 inches and dv dt equals 90, we can compute the value for dr dt. It's 1 over 4 pi times 3.9 squared times 90, which is approximately equals to 0.47 inches per second. Let's think about how we arrive at this answer. We started with a formula related v and r. Then we thought of both v and r as a function of time and differentiated each side of the equation with respect to time. We used a chain rule to get an equation that related dv dt and dr dt. This equation is called related rate formula, since it defines relationship between two instantaneous rates of change, or derivatives. Let's define the idea of a related rate formula in general. Suppose the variable a is a function of variable b. And then we think of both a and b as themselves as function of x. To get the related rate formula that defines the relationship between the rate of change of a with respect to x and the rate of change of b with respect to x, we differentiate both sides of the equation with respect to x. On the left side of the equation, we get dA dx. On the right side of the equation, we have a composite function. Because f is a function of b, which is a function of x. So we need to use the chain rule. First, we differentiate the f with respect to b, and then multiply by the derivative of b with respect to x. This resulting equation is called a related rate formula. So now let's work through a little bit more complicated related rate problem. A baseball diamond is a square with each side of 90 feet in length. Suppose that at the exact moment the ball is hit, Luke runs from first base to second base at a constant rate of 20.7 feet per second. Our question is, what is the rate at which the distance between Luke and home plate is changing when Luke is 35 feet away from the second base? To answer this question, we first introduce some variables. Let x represent the distance from first base to Luke's position in feet. And let y represent the Luke's distance from home plate in feet. Since Luke is running at a constant rate of 20.7 feet per second, and since x represents Luke's distance from first base, then dx dt equals 20.7 feet per second. Our task is to compute dy dt when Luke is 35 feet away from the second base. So this will happen when x equals to 90 minus 35 feet, or 55 feet. To answer this question, we first need to define an equation that expresses the relationship between x, Luke's distance from first base, and y, Luke's distance from the home plate. If we watch Luke run and think about the length of x and y, we can see that these lengths form two sides of a right triangle with first baseline, which has a length of 90 feet. And the Pythagorean theorem tells us the relation between these three lengths, specifically x squared plus 90 squared equals y squared. We can get a relation between dy dt and dx dt if we differentiate each side of the equation with respect to elapsed time. To do this, we need to first think x as a function of t and think y as a function of t. Then, using the chain rule, the derivative of x squared of t is 2x times dx dt. Derivative of 90 squared is 0. And the derivative of y squared is 2y times dy dt. Now we have an equation that relates two rates, dx dt and dy dt. And I'm going to divide both sides by 2y to get dy dt by itself on the one side of the equation. And then we can cancel 2's to simplify. We have a value for x and a value for dx dt. So we can compute a value for y, then we'll be able to compute for dy dt. To do this, we can go back to the Pythagorean theorem. We want to know value for y when x is 55 feet. Once we calculate and solve for y, we get that y is approximately equals to 105.5 feet when x is equal to 55 feet. Let's put all this together. We were given that dx dt is 20.7 feet per second, and we want to do this computation when x is 55 feet. And we figured out that when x is 55 feet, then y is approximately 105.5 feet. So now we can compute the value for dy dt, which is the rate at which the distance between Luke and home plate is changing when Luke is 35 feet away from the second base, as approximately 110.8 feet per second. So in this scenario, we used Pythagorean theorem to model the situation, thought of x and y as functions of t, time, and then use the chain rule to relate the rates dx dt and dy dt to solve for our problem.